so let me just start with what this talk is and is not about. So I'll be focusing only on lattice-based cryptography, which basically is the most promising post-quantum crypto schemes. By post-quantum, I mean like, so if quantum computers are a reality in the future, then we want kind of crypto schemes that are resistant to quantum attacks, and lattice-based crypto are kind of the most promising. There are several other candidates like code-based crypto, multivariate crypto, which I'll not be talking about. So there are other candidates, and I'll be only serving a tiny fraction of the work that has been done in lattice-based crypto. Of course, it has been like 20 years of research, and I cannot cover that in one talk. So I'll just kind of give a flavor of what lattice-based crypto is about. And this talk has nothing to do with quantum computing, so there'll be no quantum in here. But of course, I'll be mentioning many problems along the way that are difficult to solve even using quantum algorithms. So like we don't know any efficient quantum algorithms to solve these problems. Okay, so what is a lattice? A lattice is this grid-like structure where you are given some basis vectors, let's say in this, so v1 to vn, and a lattice is formed by integer combinations of these basis vectors. So you take all possible integer combinations, you get this lattice. So for example, here you see a picture of a two-dimensional lattice where the basis is v1 and v2, and as you can see, all integer combinations like 2v1, 2v1, v2 minus v1, v1 plus v2, etc. are all in the lattice. So a lattice is defined by all integer combinations of these basis vectors, and we call n the dimension of the lattice. Okay. So for a given lattice, the basis is not unique. So there can be different bases for the same lattice. For example, for this particular lattice, v1 and v2 is a basis, and v1 prime and v2 prime is also a basis. So for this talk, I'll be calling the basis that looks like v1 prime, v2 prime, in the sense that the basis vectors are kind of orthogonal to each other, like they're close to orthogonal, as a good basis, and the basis that like basically like v1 and v2, where you don't really see the structure kind of when you look at the basis, as a bad basis. So I mean, in this picture, I mean, if you look at v1 and v2, you will still be able to, after some time, figure out what the structure of the lattice is, but think of it in n dimensions. If you have a basis that looks like that, you'll kind of, it will be very difficult to get a clue of what the lattice is actually, just by looking at the basis vectors. And that's kind of what is the main reason why these lattice-based problems are hard. So what are the hard problems in lattices? So the most fundamental kind of problem that has been considered in this is the so-called shortest vector problem, where you are given the basis of the lattice, and you are asked to find the shortest non-zero vector in the lattice. So I'll denote the length of the shortest non-zero vector by lambda 1. So in this picture, basically this green vector out there is the shortest non-zero vector, and if you are given a basis, your goal is to find this shortest non-zero vector. So in 2 dimensions, there are efficient algorithms to solve this. There is like an efficient algorithm by Gauss from like several years ago, but if you increase the dimensions to a large number, let's say 100 or 200, you will not be able to solve this problem essentially. So an approximation version of this problem is, so given a lattice basis, you are not required to find the shortest vector, but you're required to approximate it within a certain length. So within a certain factor gamma, so gamma is some factor bigger than 1, and you are required to approximate the length of the shortest vector within this factor. So one can also define decision version of this problem, where you're given a basis and you're given some positive real number d, and you are required to decide whether the shortest vector is has length less than d, or it is bigger than gamma times d. So it's a decision problem. It's a promise problem, which can be seen as a decision variant of the approximate shortest vector problem. So there are many other hard problems in lattices. For example, like the closest vector problem, the shortest independent vector problem, and others. I mean, and I'm not going to basically go into those. So because SVP kind of will give a good flavor of what I'm going to talk about. Okay, so what do we know about in terms of algorithms and complexity for this problem? So here's a small table based on the factor gamma. So if gamma is small, so let's say gamma is less than a polynomial, so in particular 2 to the log n to the 1 minus epsilon. If this expression looks a bit scary, it's just smaller than a polynomial. So essentially, so if it is smaller than a polynomial, then the problem is hard. So it's hard to solve, like NP hard. And if this factor is square root n, then this is known to be in co-NP. So of course, this problem is very easy to see to be in NP. So it's just trivially in NP because the witness is just the short vector. But it takes quite some work to show that it is in co-NP. And you can actually show that when the factor is larger than square root n, then it is in co-NP. The crypto is typically based on basically this problem when you talk about polynomial approximation factors. So gamma is polynomial in n, and this is kind of the regime where cryptography is based on. So and the best would be something like n. And this problem, I mean, basically we don't know of any efficient algorithms to solve this if the factor is even sub-exponential. So the best, so the best approximation factor for which we have an efficient algorithm are exponential factors. So in particular, if the gamma is 1 plus epsilon to the n, then we have that this problem is it can be solved in polynomial time. N is the dimension of the lattice. Yes. So in particular, the fastest known algorithms for this problem, I mean, this is a general result. So if gamma is, let's say, r to the n over r, then the fastest known algorithms run in time 2 to the O of r times poly n. So it's really, so in particular, if gamma is polynomial in n, then the best running time is exponential in n. And so in a couple of recent works, we showed that essentially the fastest known algorithms for this problem for gamma like close to 1 is essentially 2 to the n plus little o of n time. So they run in almost 2 to the n time. And in another work, we've shown that essentially basically there is, if you believe what is the so-called exponential time hypothesis, actually a variant of this called the gap exponential time hypothesis, then no algorithm can solve this problem for approximation factor close to 1 in time better than 2 to the constant times n. So for some there exists some constants that you cannot solve it in time better than 2 to the constant times n. Note that this does not directly influence crypto, but because the crypto is basically dependent on factors which are polynomial in n, but we don't know of any better algorithm to solve this problem when the approximation factor is polynomial in n. So the only way we know how to solve it is to solve the exact problem. And so in that sense, if you believe that that's the only possible way to solve it, then essentially this result kind of says something about the security of these crypto systems. Okay, so the first applications of lattices included attacking these crypto systems. So lattices were not initially being used to build crypto systems, but to attack these. This started even back in the 80s, and people started to use lattices to construct crypto systems in 1996 after this breakthrough result by Aitai. And cryptography based on lattices have many advantages over traditional cryptography like RSA. For example, it has strong mathematically proven security. So the security is based on like worst case to average case assumptions. By mathematically proven, I mean under the assumption that these corresponding lattice problems are hard. And it is believed to be resistant to quantum computers. Basically, the quantum algorithm, for example, the Shor's algorithm could factor RSA because it could exploit the algebraic structure, underlying algebraic structure. But since this problem looks very geometric, it doesn't look like quantum algorithms would have any significant advantage in solving these problems. So people believe that these are resistant to quantum computers. Of course, it is a belief until someone breaks it, basically. But for now, people don't have any approach to solve this in using quantum algorithms. And in some cases, actually, these are much faster. I'll discuss a little bit about these timings at the end of the talk. But there are current implementations that are very fast for these lattice-based crypto systems. And we can do many more primitives. We can construct many more primitives, crypto primitives using these lattices. For example, we can construct fully homomorphic encryption, which was basically first constructed using lattices. So there are, I mean, almost like everything that you can think of in crypto you can construct using lattices. So this is a small list. So public key encryption, chosen ciphertext attack, public key encryption, identity-based encryption, oblivious transfer, circular secure, sorry, encryption, hierarchical. I mean, this is like a small list, but almost anything you can think of in cryptography you can do via lattices. And I will not be constructing this whole list, but I'll just give a small sample. So first I will talk about the first kind of candidate of public encryption scheme, which was back in 1997 by Goldreich, Goldwasser, and Halevi. So the reason I talk about this because it's based on a very kind of easy to explain principle, and even though that particular scheme was broken soon after, the basic principle has been used to construct future schemes, and it still kind of is being used. So I will get into that, and then I will talk about basically the two main problems on which lattice-based crypto systems have been constructed. So one is the short integer solution problem, and one is the learning with errors problem. So most of lattice-based cryptography has been constructed assuming the hardness of these two problems. And then I will at the end talk about the recent implementations. I'll give a brief overview of what are the recent implementations of these lattice-based crypto systems. Okay, so I go over the GGH public key encryption scheme. Okay, so what is public key encryption? Suppose Alice wants to send a message to Bob over a public channel. So the channel is something that anyone can see. So Bob generates a pair, public key and the secret key. So it generates a public key and secret key pair, and then Alice uses Bob's public key to encrypt the message that Alice wants to send to Bob. So Alice sends a ciphertext, which is encryption of public key with M, and then Bob obtains the message by decrypting this ciphertext using the, I should say that should be decryption of C, but yeah. So Bob obtains the message by decrypting C, and the security is based on the assumption that like essentially no eavesdropper, given the ciphertext and the public key, should be able to obtain any useful information about the message. So, and another very important cryptographic primitive is the digital signatures. So suppose you want to sign digitally the message M, in the sense that you want to basically authenticate this message so that no one is able to forge it, but everyone using your public key can verify your message. So in this procedure also we require a key generation. There is a key generation algorithm where the algorithm generates a pair, a public key and a secret key, and there is a signing algorithm. So the signer basically uses the secret key to sign the message and produce a tag, and anyone who has access to the public key can verify this, can take the tag and the message as input and check using the public key whether the tag is a valid tag or not. And no one should be able to forge the signature given a valid signature and the public key. So this is kind of the security assumption. Okay, so now where do lattices come in? So let me just describe one basic thing about one basic kind of about lattices. So how do you reduce a vector modulo a basis? So you are given a basis and you want to reduce a vector. So you look at that vector up there in red. Essentially, you want to reduce this modulo this basis. So what you do is you construct essentially this box equally congruent boxes around each lattice vector, and using this basis. So basically, you take all the next lattice vectors, you just bisect the line, and you get a parallelogram. So U modulo this basis is basically, if you look at U is an integer combination of these, so U is a point in the space, it's not a lattice vector, and you want to reduce it modulo this lattice. So what you do is you write it as a linear combination of these basis vectors, and then you just take the closest integer to each of these coefficients. And when you do that, you basically, so for that particular point up there maps to this point close to the origin. So any point in the space will map to one point in the parallelogram around the origin. So So this is kind of the very basic procedure. It's very easy to kind of do this, and this will be very useful in what I'm going to talk about next. So, right. So, okay. So when we reduce a vector modulo a bad basis, so a bad basis kind of, I mean this parallelogram around the origin is kind of has very long edges essentially, and in particular a vector falling in this parallelogram can be very far away from the origin. So you don't really know how it behaves. So in particular this u modulo b is likely a very long vector. So it's with very high probability it's a long vector if you pick a random vector in the space. And on the other hand, when you do it with modulo a good basis, since the good basis has very orthogonal looking kind of basis vectors, so when you take this vector modulo this good basis, it lands within some small distance from the origin. So it's close to the origin, and I will be exploiting this idea basically that essentially I repeat. So when you take a bad basis and you take a random vector modulo a bad basis, you will get something that is a very long vector very far away from the origin. Whereas if you take a random vector modulo a good basis, you will get something that's close to the origin. Sorry. Okay. So u minus u mod b. So u mod b is the reduction modulo this basis. Sorry. So this u modulo b is a short vector, and so if you take the difference of these two vectors, you will basically get this particular this particular vector. So this is the lattice vector you will get if you take the difference of u and u modulo b, which is the difference of this vector and that vector. You will get the lattice vector. You will get exactly this particular lattice vector, which is basically very close to the original starting vector. Okay, so how do you use this to basically encrypt a message? So you map the original message to a vector close to the origin. So you map it using some mapping to a vector close to the origin. So you have a vector which is, and then what you do is you encrypt it using a bad basis, which is the public key. So the public key is some bad basis of this lattice, and you essentially take the original message modulo this bad basis, and when you do that with very high probability, as I said, it will go very far away from the origin. And so the decryption is exactly the opposite. You take the secret key is some nice basis that basically gives away the structure of the lattice, and when you kind of take the ciphertext, which is some faraway vector in the lattice, and you take it modulo the good basis, you will get something very close to the origin, which means you will basically get the original vector. Of course, I am hiding many details, but I mean basically given the appropriate distribution of the original vector, if you start with some vector close to the lattice, you will end up with, if given a good basis, you will end up with the vector, with that particular vector when you basically do this decryption. So again, encryption, you take the original vector, you take it modulo the bad basis, it gets very far, and you don't know what the original vector is given this particular vector. So given this far off vector, you cannot really compute what this vector is. You don't know where the how to map it back to the original vector, but given the nice basis, we can easily kind of do that. Just take it modulo the nice basis, and it will get you a vector which is close to the origin, which means basically it will be the original vector. So if it is really close enough, it has to be the original vector. Okay, so exactly using the same principle, there is a dual signature scheme. For basically, what you do is you use the secret key, which is the good basis, and you basically first of all you map the message to a random vector in space. Now it's not something close to the origin, but some random vector in space. And then you sign it using you take the difference of this random vector with this random vector modulo the good basis. So when you do that, you get something, you get a lattice vector which is very close to the original vector, which was far away in space, which was randomly in space. And then what your verification procedure, you just look at the public basis and you check whether this vector that you got is actually a lattice vector. So this is easy to check. You just check whether it's in the linear span, it's in the integer span of the basis vectors, and then you check whether the difference of this t minus m is actually short. So if it is short, that means that basically it is indeed kind of the valid signature. Okay. So as I said at the beginning, I mean this particular scheme was broken. I mean by Fong and Guyan in 1999 pointed out there is a serious flaw in the scheme. Essentially showed that if every ciphertext reveals information about the plaintext, so even if given one ciphertext, you cannot really recover the plaintext. If there are many of them, you will be able to kind of figure out information about the plaintext. But the principle, the basic principle, which is to map these using the good basis and the bad basis, has been used in some form or the other, basically in several follow-up schemes, and is even being used today. So I just wanted to point out this because it's very simple to kind of explain, and it illustrates the strength of these lattice problems. So in fact, the first fully homomorphic encryption scheme candidate by Craig Gentry in 2009 was based essentially on the same principle. Okay. So now next I talk about the short integer solution problem, which was basically the starting point of lattices being used in cryptography and has been used to design many crypto systems. So the short integer solution problem, okay, so first of all, this is a motivating example. So collision resistant hash functions. What are collision resistant hash functions? It's a family of functions indexed by some kind of C, and such that for any efficient algorithm that outputs a pair x1, x2, the probability that this is basically the hash function maps these two x1 and x2 to the same value is small. So in particular, it is hard to produce a collision. For a randomly chosen C, it is difficult to produce a collision, and this has many applications in cryptography. So it's an important construction to come up with collision resistant hash functions. And so here's a kind of construction for collision resistant hash functions. So what you do is you basically have n as, let's say, the security parameter. So security parameter means basically you want to say that the probability of getting a collision is negligible in this n, and you choose m and q. Q is some polynomial in n such that m is bigger than n log q, and then the hash function is indexed by a matrix of zq to the n cross m, and the hash function basically takes a secret s, which is an m bit string, it's m bits, and maps it to m times s in zq to the n. So we start with a bit string and we map it to zq to the n, such that, so basically q is s1 times m1, m1 is the first column, s2 times m2, and so on, mod q, where mi is the ith column. Okay, so this essentially motivates the definition of this problem, the short integer solution problem. So this is basically you are given a matrix, it's the same structure, and you want to produce a vector in -1, 0, 1, such that mx is 0 mod q. Notice that if this restriction that x is in -1, 0, 1 was not there, then this is just an easy problem. You just have to come up with some x so that mx is 0 mod q. This is easy. This can be solved using linear algebra easily, but if you want to really get a short vector, then this is a difficult problem. And the problem of finding collision in collision resistant hash functions is essentially the same as this problem. So all you need to do is to find if you find a collision, you basically find s1 and s2 such that ms1 is equal to ms2 mod q, which is essentially saying that you take the difference of s1 and s2 and you solve this problem. So s1 minus s2 is in -1, 0, 1 to the m, and that essentially solves this problem. So So this problem directly does not look like a lattice problem, but it can be expressed as a lattice problem. You can essentially define an integer lattice, which is just this lattice given by z belongs to z to the m. So integers m length integer so an integer lattice of dimension m, such that m times z is congruent to 0 mod q. So this defines a lattice, and short solutions to this particular, the short vectors in this particular lattice give solutions to the short integer solution problem. So if you can solve this shortest vector problem in this lattice, then you get solution to the SIS problem. I'm like hiding some details, but essentially there is an equivalence. In fact, there is a worst case to average case reduction. So what you can show is that if you can find short vectors for m being uniform, find a short vector in this particular lattice, then you can solve the shortest vector problem, the approximate shortest vector problem for approximation factor polynomial in n on any n-dimensional lattice. So this is very surprising. So you can reduce the problem of basically this randomized problem to a hard to a believably hard worst case problem. So, and this was kind of the main big contribution of ITI, which was this worst case to average case reduction. So you can solve, if you solve this average case problem, you solve these worst case problems on lattices. Okay. So there is a generic procedure to obtain a digital signature from any collision resistant hash function. So there is some generic procedure, and hence we get that immediately gives, because I just showed that you can get a collision resistant hash function from this short integer solution problem. So you can get also a digital signature scheme, but the digital signature can be constructed more directly and more efficiently from SIS. This was done by Gentry, Pikert and Vaikunthanathan. I will not show the scheme, but the construction is also based on an idea similar to the GGH scheme that I presented, except that the lattice is chosen more carefully to avoid the attack that Fong gave. Okay, so however, unlike GGH, this is secure under the inhomogeneous SIS assumption, and hence under the assumption that gap SVP poly n is hard in the worst case. So this construction cannot be broken until unless you really break this hard lattice problem, unless you solve this hard lattice problem. So it is secure under the assumption that this problem is hard. Okay, so next I go to the learning with errors problem and its applications. Okay, so learning with errors has found even more applications. Actually, it's an even more important problem. So this is the problem. Basically, the learning with errors problem. So the search problem is you want to find a random secret S, which is an element of ZQ to the n, given a matrix in ZQ to the m cross n, and A times S plus some small error. Notice that if this error was not there, then this problem is easy. You can solve it using Gauss elimination. You basically are given a matrix and you are given A times S. You just want to find S, which is easy. But with this error, this problem becomes much harder, and we don't know any efficient algorithm to solve this problem. So the decision problem is you are given this pair A comma B, and you want to distinguish this from a totally uniform pair. So A is just this uniformly random matrix from the same distribution, and U is a uniformly random vector in ZQ to the m. So given this, this AS plus B really looks like a uniform vector. This is what basically saying that this decision problem is hard to distinguish between these two means that essentially this A times S plus E looks like a uniform and independent vector. So you don't really learn anything about S from this. And again, there is a worst case to average case reduction known. So in particular, if you can, so for a lot of crypto systems, you can break crypto systems. You need to solve for breaking cryptosystem you need to solve this decision LWE problem, and there is an easy reduction from search LWE to decision LWE, which means if you can solve this decision LWE problem, you can also solve the search learning with errors problem, which was the first one where you want to find the secret. So if you can distinguish these two, you can also recover the secret from this pair. And there is a reduction from the lattice problem, the shortest vector problem with approximation poly n, to this LWE problem, which means if you can solve the search learning with errors problem, then you can also solve this hard lattice problem. Okay, so I'll describe the simple public key encryption scheme from under the assumption that this decision LWE problem is hard. The scheme is from a result by Oded Regev in 2005. So okay, so this is a simple scheme. I just want to, let's say, encrypt one bit. So I want to encrypt a bit with mu, which is either 0 or 1. So Alice wants to basically send it privately to Bob over a public channel. So Bob chooses basically all these parameters q, m, n, a, and s. So a and s are uniformly random from their respective domains, and e is an error distribution chosen from the basically the error distribution corresponding to the learning with errors problem. So essentially it's some kind of small errors. So typically it's chosen using the Gaussian distribution, but I'll not get into what the distribution of this error is. So in this case, the public key is this matrix A and this vector B, which is A times S plus E. And as we just said, that basically there is no way to, we don't expect to recover S from this, so we don't expect to recover our secret from this public key, and the secret key is this vector S. So how do you encrypt the message? What you do is you pick a uniformly random m bit string R, and then the ciphertext is basically just computed by multiplying this R with A and also multiplying this R with B and adding a small offset, or adding basically mu times q over 2. So basically if mu is 1, then you add q over 2, if mu is 0, you add nothing. Okay. So so how does this help? If you want to decrypt your to get back your message bit, what you do is you look at the second second part of the ciphertext, and you subtract so you have the secret key, so you subtract the first, so you subtract from the second part the first part times S. So when you do that, so this R times B cancels with R times A times S, and what you are left with is R times mu times q over 2. So in particular, if mu is 0, then this is 0, and if mu is 1, then this is close to q halves. So you can essentially recover. I'm sorry, I missed the error part. So there's R times E plus mu times q over 2 is what is left. What is left when you do the subtraction, and essentially if mu is 0, then this, because the error is small, so R times E is small, so it would be close to 0 what you will get at the end, and if mu is 1, then what you would get would be close to q halves. So you would be able to look at it and tell whether it's an encryption of 0 or encryption of 1. So this was possible given the secret key, but like without knowing this S, it would not be possible to recover this bit. Of course, this is just a 1-bit encryption, and it's not so efficient. There have been much more efficient candidates construction, and I'll just speak about it in a moment. But this is the simplest kind of illustration of a public key encryption based on learning with errors. And so if you found my previous kind of description about with this picture a little bit vague, this is more mathematically precise kind of construction. So the security is almost immediate from the decision LWE hardness assumption, So basically, if you have that AS plus E looks random given A, then of course if you add this small offset, it would still look basically random. And multiplying this R, basically you can deal with it using the leftover hash lemma. I mean, it is easy to see. Maybe almost immediate is a bit of an overstatement, but essentially with some work you can get that this is secure under the decisional LWE hardness assumption. Okay, so how do we make this learning with errors more efficient? Okay, so for the learning with errors, so to get one pseudo random element Pi in ZQ, we require an n dimensional inner product. We have to multiply a n dimensional vector with another n dimensional vector. We have to take the inner product to get one pseudo random element. So cryptosystems basically must have a key size at least n squared log q, because n squared matrix elements times log q. So, and like you would hope that maybe taking one inner product would give you n pseudo random elements. Like that would be ideal, because then essentially you would have a much more, to get the same amount of pseudo randomness, you will need much smaller number of you need much smaller key size and so on. So it would be much more efficient. So if this was possible, if something like this was possible, then we would get n pseudo random elements in ZQ from one inner product and not n inner products. And this would replace every n squared length key by a key of length n. So we would save a factor of n, which is huge actually. So the question is how to define the star operation that I mentioned. It's like something hypothetical that I wrote here. And since we have a small error, if we do this multiplication coordinate wise, it's not really secure. So in particular, if I want to say that B1 is A1 times S1 plus E1 and B2 is A2 times S2 plus E2 and so on, then this is not really secure. So we don't want to do that. So this motivated the definition of learning with errors over rings. So we look at this ring, which is integers polynomials modulo the polynomial x to the n plus 1. So and you take this ring modulo q. So q is again some integer, a large integer, which is polynomial in n, and then operations in RQ are very efficient using algorithms similar to FFT, and so FFT is fast Fourier transform, so you can basically do operations quite quickly in this. And now the search problem is you want to find the secret S in RQ given this pair. So these pairs A1 comma A1 times S plus E1, A2 is B2 is A2 times S plus E2 and so on. So note that we are, as opposed to what I just said in the previous slide, now we are using the same S because it's not really a single element, but this ring element. And this we believe is kind of hard to solve. So the decision problem is defined similarly. You want to distinguish this pair AI BI from a pair AI and a uniform element in RQ. And so again there are worst case to average case kind of reductions. So in particular, if you can solve this problem, then via a similar chain of reductions you can solve the approximate SVP problem on ideal lattices. So these are basically the Euclidean lattices that I mentioned, along with some algebraic structure. So they have some additional algebraic structure that, by the way, could be exploited for potential attacks, although it hasn't been so far. So we know that if we can solve ring LWE, then we can also solve SVP on ideal lattices, which I just mentioned. The other direction is unknown, which means in case of the standard LWE, the other direction is quite easy. If you can solve SVP, you can also solve this learning with errors on these lattices. And in this case, the other direction is known. In fact, there has been some progress to solve ideal lattice, to solve the shortest vector problem on ideal lattices. So there was a recent chain of results that gave a quantum algorithm for solving this problem. if the approximation factor is 2 to the square root n log n. I mean, that approximation factor is large, but it still could kind of potentially be a threat to crypto, except that as I said, there is no real reduction from the ring learning with errors to the SVP on ideal lattices, which means that this attack does not carry over to the ring learning with errors problem. So this does not say anything about the hardness of ring LWE so far. Maybe in future, basically there can be ideas from this that can be used to solve this problem. So there is more algebraic structure in ring learning with errors that can possibly lead to quantum attacks, but so far there has been like little success actually. So ring learning with errors based crypto is more efficient, but maybe less secure. I mean, basically because there is more algebraic structure, so probably it's more likely to be attacked than the standard LWE. Okay, so I'll end my talk with this, with some of the recent implementations of these lattice-based crypto systems. So I'll just describe what are the recent implementations. So in particular for key exchange, which is equivalent to public encryption, there was this so this work by, I forget the authors, but ring learning with errors based key exchange, which has been implemented. And then this is the most popular kind of implementation. This is by this is called New Hope. It's so by Google and probably some others, I mean, basically have implemented this, the optimized ring learning with errors key exchange with conjectured 200-bit quantum security, which means that any algorithm which will break this will require at least 2 to the 200 time almost. So this is comparable to or even faster than, I mean, basically current elliptic curve Diffie-Hellman. So it's faster than almost anything, any other crypto system that is known, in addition to the fact that it provides quantum security. So in particular, the elliptic curve Diffie-Hellman, which only provides 128-bit classical security, and it's completely broken if you have quantum algorithms. So it's even faster than that. So Google has experimentally deployed New Hope plus. So Google basically kind of used a mix of New Hope and elliptic curve Diffie-Hellman, which in some way that I'm not sure like how secure this is, but probably they know what they're doing. So, and then there's another implementation for those who are kind of skeptical about ring learning with errors. Frodo says remove the ring. So he talks about plain learning with errors problem, and they do key exchange with using the plain learning with errors with some optimization, and they conjecture not 200-bit security like New Hope, but 128-bit quantum security. And this is still, I mean, this is slower than New Hope, so about 10 times slower, but still almost as fast as the elliptic curve Diffie-Hellman. So it's still very fast. So and they're saying that like, if you don't believe in the security of ring learning with errors, you believe that it could be broken, so then you could probably go for this one, which is, I mean actually if it's as fast as elliptic curve Diffie-Hellman, it's still reasonably efficient. You don't need to I mean you don't want more efficiency at the cost of security if you can help it. So then there is another implementation based on this super singular isogeny Diffie-Hellman assumption, which is as so far resistant to quantum attack. So there is no quantum attack on this special kind of Diffie-Hellman assumption. And then there is NTRU, which also has not had any quantum success. And then there are these other digital signature schemes. So one of the first ones was Bliss. It was an efficient digital signature scheme based on works by Lyubashevsky. And then there is Dilithium, which kind of which kind of tries to eliminate some of the vulnerabilities that were there in this scheme, the Bliss, and it's almost as efficient and hopefully more secure. It's more recent, so I mean all these, I mean the security of all these more recent schemes have to, I mean, bear the test of time essentially. So one can say more about their security only when no one has broken them for several years. So and then there's another implementation by Shai Halevi and Victor Chup, and its implementation. So this is basically implementing fully homomorphic encryption, not so which is usually much more inefficient. So that people are trying to even implement these fully homomorphic encryption schemes, which has many more applications, but so far all the constructions are quite inefficient. And then Crockett and Pikert have a high-level framework aimed at advanced lattice-based crypto systems. So in particular, this long list that I mentioned at the beginning, they try to implement all these advanced crypto systems and not just the basic ones that I talked about, like public key encryption and digital signatures. So there's tons of ongoing work. I mean, basically there's a recent call by NIST, the National Institute of Science and Technology, for proposals for new post-quantum crypto systems. So probably in a few years there'll be many more candidates and many schemes broken, and probably some will survive. So I mean, we'll know more about this in the next few years, hopefully, once this kind of these proposals are evaluated. So that's all for my talk. I'm happy to answer questions. Too technical?
Yeah. Very naive question.
Okay.
If you want to use this type of cryptography, how large should be n? Because you often talk about n function. How large should be?
So it's n should be essentially the same as the security parameter that I talked about. So it should be, in particular, if you want, like, let's say 200-bit security, you take n to be maybe a little bit larger than this, but about that size, because you don't want any algorithm to solve this in time faster than 2 to the lambda, where lambda is the security. So in practice it should be a few hundreds.
Okay, I have another naive question. So, I mean, for quantum algorithms, like when one of the key techniques is this Fourier transform, right? Which work in the case of
Factoring and
which uses this some kind of periodic. Yeah. So I mean, and these lattices look like something periodic as well.
yes.
So I mean, it's just that why is it that the quantum algorithms, the Fourier transform basically, which could attack.
Yeah, I don't have an answer to this question. No. I mean, yeah, I guess people tried and failed is all I can say.
Yeah. Right. Yeah.
Yes?
So in one of the authentication skills, you
Yes?
say that
Should I go to the slide or?
yeah, in the slide, R is chosen randomly, but I don't know what you mean by that.
This one?
Even before that. Yes, here.
This one?
When you say that it maps to a random vector space, how do you do that? How do you map them?
Okay, I mean, so you want to, I mean, it's not actually, I mean, random in space is, of course, it's not possible to do it. So you have some kind of distribution of, so that it's random in a large enough kind of box essentially, and you don't really map it in the space. It's infinite, of course. You don't want to do that. So when I say a random vector in space, you pick a large enough box so that it behaves like a random vector, and you want it to be random with respect to the lattice. So as long as you pick the box big enough, and you take something random within this box, you'll end up with a random vector in the lattice.
You take it from a subspace of the.
Not even a subspace; it's just a subset. I mean, basically, yeah. So I mean, all you want is that it should look random with respect to the lattice. So as long as your bounding box that you are basically choosing is large enough, it will look very random in this.
Any more questions? Okay, if not, then let's thank our speaker again.
Okay.